It's the second one from top.
On which side?
Left side.
So I was going to write something on the board. Saturday. Spirit of Mark, right? I just thought I'd write down a few topics. So you put in teaching astrobiology, abbreviation for astrobiology. Two, I just bring down some of the things we've heard about today. What you might call the interstellar Earth connection. And then there's this very exciting bit which you might call the Great Divide, which is how you get from biochemicals to biochemistry, which you might call life. And there you have, of course, you have the input of bioorganic chemistry, which we heard about in the first talk. But we also have something which I know is studied here, which is mathematical biology. They obviously play a role, and we might like to discuss what those roles are. And then, of course, there's other things, the development of life on Earth. I don't think, because there's not very many biologists here, that they can certainly make a useful contribution to thoughts about this, but not so much for physicists, I suppose. And then, of course, there's the influence of space missions. I don't know how many people here are involved with space missions, but obviously Denmark plays a role in space missions and other Nordic countries. There's a number of other topics which I think may be coming up later, things like panspermia, which is related obviously to radiation damage. There's also a spin-off in other areas. Surviving the delivery to Earth of, say, bacteria, which may sound a bit hairy, but actually bacteria from the Earth are convected up into the upper atmosphere and then have to re-enter the atmosphere. So that's a way of getting bacteria going around the Earth. So actually the question is quite an interesting one, even if it doesn't relate to panspermia. So, well, this is just a few thoughts about how we might start a little discussion about some of the things we're hearing today. I thought maybe it was fair to start with teaching, since we just had to talk about teaching, and I know there's some people here who've got experience in that. Is Big Eva not? No. Oh, pity, because I know she's 50 years old. But perhaps some of the people who are involved with teaching in the Nordic countries, teaching, apart from Harry, that is, would like to make comments about what Harry had to say. Is there anyone here who's involved with the teaching still who's actually left?
I have a question for you.
Yes, please.
Have your research, is that within astrobiology, or do you only teach astrobiology?
Well, one of the things I'm studying is stability of planetary systems. It's astronomy.
Yeah, but
Has to do with impacts, or for example?
No, about longer time stability, mainly the migration of planets.
Yeah.
Could you perhaps enlarge on what the migration of planets is to people here? Because I think probably it might come as a bit of a surprising phrase to some people.
There's
Well, does it? I mean, you always think Jupiter was where it always was? Or? I mean, most people did until recently.
the problem about migration of planets came about when the first extrasolar planetary systems were found. And it turned out that many of the giant planets that orbit these stars are much closer than the orbit of Mercury. And based on the theories, cosmogony theories, there should be no planets forming that close to the star. Now one question was how to get these planets close to the star. And there have been various models of jumping Jupiter that form interactions between Jupiter-sized models or friction in the accretion disk that form the planetary system. So we're looking now at resonances between two planets, how we can get the friction kind of affects the outer planet, and due to resonance it moves in and gets the inner planet into resonance and starts to push the inner planet also. So this is one of the things we're studying in this planetary migration. So planets can move about due to various effects.
So this means that the nice idea that the most condensable things form closest to the sun and less condensable things form further away, this all goes out the window, does it? Because that sort of makes sense.
No, it's to keep that, right? It's to make
I
sure
mean, our
that...
solar system is still here.
Yeah.
Yeah, that's right, yes.
No, I mean, isn't the migration and then to sort of keep the old theory that gaseous planets form far away from the star, but then
they're coming inwards.
Yeah.
Okay.
So it's to keep our picture.
Okay.
But there can be, it's a little bit more complicated because there can be also migration outwards.
Yes, well, you need migration outwards because these hot Jupiters are far too close to the sun. I don't know if people know this, that the reason that the first planets were discovered was because they weren't Cuban. Because everyone assumed if you had to find a Jupiter, it had to be a Jupiter, because massive and otherwise, the period would be several years at least, so you must look for fluctuations over a period of several years. And then Maya, the Pontifical Provence, just happy there at time actually, when he, just after he discovered it, it was quite exciting. Discovered this thing with a period of a few, what's it, days? 5 days. And of course the reason people hadn't discovered planets before was they were looking for the wrong signature, which is very interesting. And so that's how it all started. Now there's how many extra solar planets? I don't know.
119 yesterday.
119 yesterday. 119 and rising. I don't think that these places that take bets on anything would take a bet on anything less than 200 in a couple of years now. So, well, I mean, I didn't write extra solar planets down, I think we hadn't mentioned them, but obviously there are other great impetus. If you were to say, what has really made this subject, brought the subject alive suddenly, astrobiology, is partly because we have the tools for doing it. We can start doing real factual observations now. Things like the VLT, the Hubble Space Telescope, and also particularly the laboratory techniques of micro-Raman and so forth, the ability to look at very fine detail and meteorites, detect, for example, that there's more L and D than antimony and amino acids, things of that sort, have really made the subject really come alive in the last 10 years, or less really. And there's many such things. Of course, extrasolar planets is one of the big things which really push and got people really excited. So definitely on a list of things to do with astrobiology. But what about this interstellar Earth connection? Because there's something there where I think that the real physics could be very useful. One of the things really not understood at all is if you take micrometeorites, say 10 microns in size, of density of 1 or 2 centimeters, and you bring them in through the Earth's atmosphere, and they're packed in biochemical according to what we see in literature. Why do they survive the atmospheric entry? Because theories say they shouldn't. There's a nice bit of physics to do there. I don't know if people work in that kind of area where they could address problems of that sort. Because it's not clear why they don't melt an awful lot more than they are known not to from observations. You can pick them up in the Antarctic, and there's about 70% of them are not really melted much at all. And according to theory, they'll be much more melted. So the people in this room who feel they have the kind of tools to address that type of problem, because that's quite a real physics problem which is not solved and is very important to understand, I think, really. The re-entry problem.
Why should they actually melt?
I'm sorry?
Why should they actually melt? I mean,
Well,
where the heat going?
Well, let me answer the question. Let me answer the question. The question is, the theories which are used to calculate the heating at present in the entry say it should melt from the thermal capacity and so forth. Basically, they stop by the time they've displaced their weight. And in doing that, they should have melted according to theories. Now, why exactly that should be they should melt? You'd have to go into those theories. I don't know. I'm asking if people, if that turns anybody on that problem. This is quite a nice problem. It's a well-defined bit of physics. So that's the answer to the question is that they melt because that's what the theories say they should, but the theories are wrong. Evidently, yeah?
I just recently looked at a paper which was describing this recent fireball in southern Germany where some debris have been found. And as a matter of fact, they are, as far as I understood, these meteorites melt. I mean, this particular object was melted down from a couple of 100 kilos, and they just found now 3 larger debris of 1 kilo.
Yeah, that's a big
survive.
Yeah, I'm talking about the micrometeorites, just a few microns across.
Oh, sorry.
It's those. You see, if you look at the stuff that came to Earth, still comes to Earth actually. There's about 100 times more in the form of very small micron-sized particles than come in comets or ever came in comets or in meteorites. So the budget of material coming from space, the interstellar Earth connection, if you like, the budget of material falling on the Earth's surface is about 100 or 200 times more due to very small particles, 10 microns. Now that's the point of the big meteorites. Indeed, they do, yes.
But 10 microns should not melt, I would think.
No, I mean, it's like you're standing on the 10-meter thing above the water and you throw in a small little penny, right? But it's not going to hit the water the same way as you are when you sort of land.
All I'm saying is the existing theories of the entry of such particles into the atmosphere say they melt, and the observation is they don't. So you're right, they shouldn't, because they don't. Shouldn't in that sense. But it's just odd enough that they might enter into this topic in a quite interesting way if we get to this point. But perhaps we should come to this because we talk about very specifically this especially the biochemicals, organic chemists. Is he speaking?
Yes, I guess so.
We had this binary approach. You can answer that if you like. You've got some more questions about that. And biology on education. But we can actually put the factor constants and roots into that to make that bridge, which I mean, there's no real prizes in that. There's no question about that. This is the real numbers. You would like perhaps with this great device, because that's where an awful lot of interest must lie. I mean, you mentioned the mycelization approach. Are there other approaches which you think are fruitful?
Stain, right?
Stain, sorry.
Stain,
Stain, I'm sorry.
No.
Sorry, yes, I listened to you connecting. Are there other people who want to talk about it? After you gave talks, there were lots of questions that people lots of perhaps a bit late in the day, trying to egg people on. How about the mathematical side of this?
But going from biochemicals to biochemistry, isn't that a question of information storage?
Well,
It's the easiest way of storing information that can be used.
Well, what people think, I mean, what's in that? From a mechanistic point of view, it's to do autocatalysis and the generation, spontaneous generation of structure and systems, fast equilibrium and all the rest of it. But that's all just works. You actually put clothes on it, real molecules and real weight constants and real physical conditions. That's a too biological question for us people who are left behind. Well, I was trying to get a discussion here about what we heard today, but what questions would people like to raise, and what's the burning questions? Perhaps there's more questions about Europa and so forth. Well, they come back to space missions, of course. Will be a space mission, Europa.
There were comments. Now we have a sample from Stardust coming to that in a couple of years.
Yeah.
And,
Hopefully
are there any specialists in comments who can say something about the new picture which was taken of our computers? I was very surprised when I saw it, but I can't describe it.
What were you surprised about? You look just like the drawings from Tintin, you know.
Was that all surprised?
You know,
But not like him. It didn't look like that.
it didn't look like, no, but it looked like, you know, the Tintin one.
Yeah, that's true.
But it looked as though it looked like a moon, did it? It looked as
Yeah,
the chief scientist in charge of that mission, I don't know his name now, said that, oh no, it's where gases come out and these things are collapsed in. Now that seemed more likely because we think of these comets as very open structures, of dirty ice or whatever, where we get gaseous jets coming out. In fact, I think they've been seen on Cali.
Yeah.
So that seemed like a reasonable explanation of that. But the roller comets is very interesting. Well, for you know about this sort of thing. I'm sure the roller comets and so forth in the early days of the solar system. Isn't that something you?
Well, I don't know, we've been involved in models and also missions to try to figure out where the water came from the comets. So,
Yeah.
this is of course also relevant to where the life came from. The water came from comets, and there are highly evolved biochemicals in comets. And the building blocks for life came together with the water that should evolve.
I was a nice physics problem when a comet hits the Earth. How much survives? I mean, what are the inside of the comet survives? It wouldn't be good if everything just broke up into hydrogen, oxygen atoms and carbon atoms and nitrogen atoms and so forth, back where you started, really.
So what's the answer to this question?
Yes.
Well, I don't really know. It's not so easy to say what they can do. I mean, I think that it looks like water could come from comets. It seems difficult to see where it should come from. But it could also come from an asteroid to the outer part of the asteroid belt. But the geophysicist seems to tend to believe that it was here originally, without really explaining how it should have been here.
Included.
Where should it come from to be originally?
So do we actually know of any cometary impacts where the body, something solid will erupt on Earth? Or do all comets break up in the atmosphere?
All comets will always break up in the atmosphere.
All of them?
Yeah. So they never
Like shooting
life, but it's likely that the Tunguska event was a comet. And it's actually likely that a large fraction of the lunar crater are comets and not asteroids.
They don't break up.
Yeah, they don't break up.
What?
Eventually they will.
Yes. Now, and similarly with Jupiter, I mean, a lot of wrong calculations have been done at the time when the Jupiter crash, Shmokhalevi, crashed. And people were surprised how, at which height the comet actually already breaks up. and wasn't expected by many people. Is that right?
Yeah, that's time forces. All the time.
Yeah. Well, that's the break up into different pieces before it came back to
Yeah.
But even after the impact, it wasn't completely unclear what will be the severity of this impact. I thought we didn't really have any serious prediction of how these how the albedo, for example, would change on the Jupiter surface. And now we know, of course, and we saw it. We saw these.
We saw it, right? It was right on the back side.
Yeah, but then we saw it a few hours later.
We saw it a few hours later, right? So we didn't quite see it happen.
No, but what we saw is already not actually predicted by many people. So it was.
We saw the whole set of gas fairs which were never longer than predicted. What I mean.
Horse.
Yes.
Yeah.
And you can see the black spots holes through Jupiter's atmosphere, which have been left by the debris of the comet. And the holes were never longer than expected because we saw them coming from the back side and they were still there when we came.
Do you mean by holes dust?
No, I mean just, you know, you see deeper into the atmosphere, so you saw lower laying.
Yes, it is.
Yeah.
So it must have, because it's more heat, I believe.
Yeah.
So it must have been
That must have been higher temperature, right? So it was pressure equilibrium, so lower density must mean higher temperature. You get the same pressure. So it's really because it's hot.
Yeah, it's hot than
Yes, yeah.
So perhaps it will be more than expected, perhaps. If that was.
Yeah, now on the subject of Jupiter, what if it does look more like Europa actually, because it's I mean, you just touched on it very quickly. I'd say a few more words about it, Aaron, because I think it's very interesting, Europa.
It is, you can see on the surface of Europa. And what they did, that they took a walk in Yellowstone National Park and picked up some extremophile bacteria. And they went into the laboratory and froze them to 80 Kelvin, put them in vacuum, and put them under UV light. Conditions similar to the surface of Europa. And then they measured the infrared spectrum and tried to match it up with the spectrum that they measured from the surface of Europa. And these frozen bacteria had the signature of their spectrum was much more closer than any mineral they could find on the surface of Europa. So there are theories that people are speculating that bacteria could maybe live in the upper layer, so protected by the ice, but living from some sort of inorganic chemistry caused by impacts of heavy ions from iron, sulfur, and so on. They're sputtering on the surface. So there should be some sort of energy in those chemical bonds there, or that it could be in the ocean itself on the base of the ice. There was a question about whether the tidal deformation of Europa could create hydrothermal vents on the rock surface of Europe, and I think most people believe that this is not possible. There's not enough energy, and that you can see from the pattern of the cracks on the ice surface that the ice shell is very slowly rotating if you compare it to the inner of Europa. The ice shelf itself is not in complete synchronous rotation around Jupiter. There's some sort of torque on it, so it slowly rotates. That means it's completely detached from the interior, the rocky interior in Europa. So people believe that the rocky interior is in synchronous orbit. Therefore, it does not have enough energy to create hydrothermal vents. So that if there should be life on Europa, you should find another energy source in this hot water going around. So that's
the story.
That's how much I know about the speculations of life on Europa. I think the most promising is somewhere connected to the ice-water boundary. That's a favorable place for life to be if you can get the energy source. And that could maybe be these places where you have breakups of the ice. If you can create some sort of chemical imbalance on the surface, then break up the ice and thereby bring the chemicals down to the life. I think that's what most people think is the most possible way of life to be on Europa. But I think the problem is to get the energy. I mean, protection from radiation and liquid water is no problem, but the energy to sustain life, that's a bigger problem.
It's a fine balance. You have too much for it. I mean, it does introduce us to extremophiles, because talking about these things, I mean, is there anyone here who's got some strong feelings about what was said about extremophiles? We could discuss that a little bit, about what the speakers said. You've got something that you spoke against history about two classes. Could you say what connection you think maybe kind of things we're talking about has to do with speculations about life in Europa? Because I mean, this is kind of use of work on human files is made in this, right?
I don't know much about Europa and chemistry lab, but there's a lot of extreme files that can live on inorganic energy sources like hydrogen and sulfur, and iron, and other reduced metals.
There's some of the sulfur that's spotted on from iron.
Yes, geysers on iron are sulfur geysers, are liquid sulfur on the surface of iron. And so all these iron iron is shrinking because it's losing material, and it's caught up in the magnetic field of Europa. And there's this plasma sheet around the magnetic equator. And Europa passes the magnetic equator twice per orbit. So there's a lot of impact, and there's also disrupting the surface very much. So you can see that the signature of the surface itself in spectra is that the ice crystals are very, very small, and this is because it's bombarded all the time by these impacting ions. So.
But the sulfur, is it in the form of elemental sulfur?
I have no idea. I think it will be, there are some talks that it's going to be ionized in the magnetic field of Jupiter.
Perhaps we've been going over 6.5 hours of a lot of break. Perhaps we ought to not pester people anymore because they come up with crazy brainwaves. Sorry.
Just one question. Is there any Nordic involvement in the ordnance matter that is going to Titan with Cassini?
I think my city has some kind of small role in it. So I think someone designed a pressure drop or something like that or participated in it. So we'll get the data.
Audibly. You get the data audibly.
But
I think there is participation from the Armstrong laboratory in Uppsala in the Högst Cassini mission. That's what I recall.
Yeah, I think you're right. Yeah. The Space Institute there.
I don't have a question. Yeah, I mean, it seems amazing that life in the form of extra files on Earth seems to be present almost everywhere. It's first of all in air, even in the very high atmosphere, like 40 kilometers or something. And then what kind of temperature and pressure and radiation. So the question is, where on Earth are there no extreme files? Where? Molten lava. Right, that's true.
Los Angeles in the afternoon.
But molten lava, yeah, that's it.
Molten lava.
Is that actually, I mean, is that actually another joke?
I don't know if that's we are not.
So maybe it's not even true, right?
That was 1,000 degrees centigrade, I'm saying. Chemistry can't happen.
Yeah. 300,000 people on Iceland or something.
I would say the precondition for living organisms to be is that you have water, liquid water, and an energy source.
But you know, even the idea of liquid water is down now, because when I was in the Madrid meeting, it was a beautiful talk, I'm afraid I can't get it, showed how you get self-replicating RNA by putting various chemicals in. You take point of ice at minus 18 degrees centigrade.
Oh, you're talking about organisms?
Yeah, in other words, but getting to life, in other words, just as getting to life. Now, whether the organisms, cell walls and so forth, will crack up and God knows what, but just the idea of getting life at very low temperature. So making life doesn't necessarily require this habitable zone that we always had that requires liquid water. Maybe we could get it solid with ice, which expands the habitable zone.
This will be all the organisms that microbiologists work with, they need liquid water.
But you don't have liquid water in Scotland or very high up in there.
No, but you still have water at the cell. I mean,
you have
so
microorganisms that have forms to survive periods with no water.
Oh, you can find spiders up there 10 to 50 kilometers, they just freeze in states and come down again, so they go into sort of...
But to active organisms,